Good evening. Welcome to Stewart Observatory for this special edition of the Stewart Observatory Public Evening Series, which was started by Professor Andrew Ellicott Douglas in September 1922, and we've been doing it every year since. It's a special meeting because we're here on a Friday night, and we are meeting in cooperation with the Tucson Amateur Astronomy Association. They are having their monthly meeting here this evening, and because of the availability of our speaker, we did both presentations together. Though those of you who are watching as part of the Tucson Amateur Astronomy Association, after today's speaker is done, stay on because there's more for their meeting this evening. The bad news, it's raining outside and it's really cloudy. We had planned on opening up the Raymond D. White 21-inch telescope at 8:30 at the conclusion of Professor Ratra's presentation, but we're not going to open tonight. Can't get the mirror wet. Okay. So our speaker tonight is Professor Bharat Ratra, who is a distinguished professor of physics at Kansas State University, which is now in our league, right? The Big 12. So it's a fellow Big 12 school. Yeah, and a Wildcat, that's right. They're the Wildcats as well. Professor Ratra received his master's degree from the Indian Institute of Technology and his PhD in physics from Stanford University. Together with Professor Jim Peebles, he was one of the people who in the 1980s suggested the existence of dark energy, which about a decade later seemed like it wasn't so bad of a prediction. He was our colloquium speaker yesterday here at Stewart, but when we contacted him, he said, I want to talk to a high school and I want to give a public lecture. So this afternoon, we were at Basis North to teach one of their AP physics classes at noon today. And that's why we're doing this public lecture on a Friday night. The other thing I'd like to mention before I introduce Professor Ratra is he recently, just this year, received from the American Physical Society. That's the physics version of the AAS, the American Astronomical Society, the Lilenfeld Award for outstanding contribution to physics and for introducing physics to diverse communities, because he makes an effort to communicate not just with other PhDs in physics and astronomy, but with the general public, with school children from all communities and backgrounds. So we are really excited to have Professor Ratra here tonight. And he is going to give a talk on the topic, the accelerating, expanding universe, dark matter, dark energy, and Einstein's cosmological constant.
Thank you very much, Tom. That's a wonderful introduction. I hope I live up to it. So before I start, I want to point out this web page, which is connected to these cards. If you don't have one, I have more. And it's got some really nice videos about global warming, and it would be really nice for people to be discussing this more because it's going to be a problem. So I'm a cosmologist, and that means I'm interested in what happens on very, very, very large length scales in the universe, how stuff is distributed. And by stuff, I mean atoms and molecules and dark energy and dark matter, how that's distributed in space, and how these distributions change in time or evolve. And it's a great time to be a cosmologist. I mean, you've obviously know the reason for that. If you've seen photographs from the James Webb, there's just fantastic data coming in. And we're kind of in a golden age of cosmology now. And we're reinforcing two very, very striking results. So when we look out at the budget, the energy budget of the universe now, and try to figure out what it's comprised of, we know that atoms and molecules make up 5% of the stuff out there. And the remaining 95%, I mean, we basically have no idea what it is. We know it has two parts, one's dark matter, one's dark energy. And all we're seeing are the gravitational effects of dark matter and dark energy. We can't probe them any other way. And the other result that's going to probably be even more profound is that these measurements are suggesting that either quantum mechanics or Einstein's theory of relativity, or perhaps both, are incomplete, and they need to be improved upon to have a fuller description of reality. So it's a really exciting time. And this is pretty close to where I live in Kansas. It's in the Flint Hills, it's tallgrass prairie, and it's a really nice place to go hiking. So I have questions, and you can answer by putting up your hands. So how many of you have gone hiking 10 kilometers in your life? What about 100 kilometers in your life altogether? 1,000 kilometers. 5, 6, 7, 8, 10, 10,000 kilometers to 100,000 kilometers. Okay, so there is an upper limit to which you can probe length scales directly with your senses. So for those of you who have hair, I want you to reach up and grab a strand of your hair and feel it between your fingers. So is that kind of the thinnest thing you can feel touch with your fingers? So that's kind of the lower limit, right? So that typically is about, if you have really thick hair, it's about 10 to the minus 4 meters in diameter. If you have thinner hair, it's 10 to the minus 5 meters. And I have a bunch of length scales up here. So I'm going to be using meters. A typical human is about 1.5 meters or 2 meters. A meter is about 3 1/3 feet. And that's kind of the typical human scale right around here. And if you're old enough and you have enough time, maybe you can get out to 10 to the 6 or 10 to the 7 meters, but you can't go out much further. And this is in powers of 10, so it goes from 1 to 10 to the 5 to 10 to the 10 to 10 to the 15. And if you have sensitive fingers, you could get down to 10 to the minus 4 meters. And those are the only length scales you can directly probe with your senses. And that's where most people develop their intuition for physics. And the kind of physics you get your intuition for is called Newtonian physics. That applies very, very accurately on these length scales. And it doesn't work that well when things are moving close to the speed of light, or you're looking at things on very, very large scales, or in really strong gravitational fields, or you're looking at very small things like quantum mechanics is important. So out over here, relativity is more important, and down here, quantum mechanics is more important. But you've built up all your intuition over here, and so there's no guarantee that the same sort of rules of physics are going to apply equally well over here and here. And they don't, and you need to extend them. You need to extend them towards relativity here. And when things are moving slowly, or you're looking at smaller scales, then, relativity reduces down to Newtonian physics. And if you're down over here, you have to use quantum mechanics. So, I mean, it's pretty easy to think this through. So if you want to try to get to a star and understand how a star works, you're not going to walk out there. What you're going to do is you're going to take a telescope and you're going to catch an image of that and store that in your computer. And then you're going to build a mathematical model of a star and add atoms and molecules and heat it up and put in rotation and put in a gravitational field and try to produce a spectrum that you're seeing in your telescope. And if it agrees, then you try to do more sophisticated observations and you try to improve your model. But over here, if you're a toddler, you've become an expert on Newtonian physics. Otherwise, you're not going to be able to move. You can't walk, you can't crawl, you can't do anything. And toddlers don't really appreciate that this way, that they've become experts at Newtonian physics, but that's what they've become. And they're not going to become experts at relativity doing what they do, and they're not going to become experts at quantum mechanics doing what they do because they can't probe those length scales directly. And so maybe that's why people feel that quantum mechanics and relativity are unintuitive. So I want to spend a little bit of time walking out this way. For those of you who are interested in the smaller scales too, there's a really nice video by the Eames brothers, that's E-A-M-E-S, They're architects, and they made this in the 1970s. It's called The Powers of 10, and you can find it on the web. So I'm going to start here, and we could do this for masses. We could also do it for times or ages, but we don't have time for that. And so I'm going to focus on just length scales. And I'm going to use a new system of length units. Instead of the old-fashioned meter, I'm going to use the Einstein as my length unit. And that's approximately 2 meters. And I want to go from him to this little planet. And we're going to do an experiment. What we're going to do is we're going to drill a hole from the North Pole to the South Pole and build a pretty strong base here, and go and get 6.5 million Einsteins and put one at the base and the next on his shoulders and the next on his shoulders and the next on his shoulders. So if you have 6.5 million Einsteins, you'll cover the diameter of the Earth, and 6.5 is approximately 10. So that's 10 million. So it's a factor of 10 to the 7 growing from here to here. We can step out further and look at nearest star, the sun, and think about the same sort of experiment, except here we're going to have to drill through gas, and we can pile up 100 Earths, one on top of the other. And so the sun is a factor of 100 bigger than the Earth in linear dimension, or if you wanted in Einsteins, then it's about 700 million Einsteins. We can step out further and look at the Earth's orbit around the sun. The Earth's orbit around the sun, which is an ellipse, but if you average it out over the course of a year, you can think of it as a circle, and this is not to scale. So the radius of this orbit, I mean, you can do it in terms of suns. You can lay down suns one next to the other, and you'd need 100 suns to get from the surface of the sun to the Earth's orbit. In meters, that's the radius of the orbit. If you want to do this in Einsteins, you'd need 75 billion Einsteins. That's very inconvenient even in using the meter, because you have so many powers of 10. So astronomers who study planetary systems use a new length unit, and that's the astronomical unit, or the AU. And that's just the radius of this orbit around the sun. Another better unit is to use light travel time, and the reason for that is very well known. Light has perfected cruise control in vacuum. It always travels at exactly the same speed, no matter what direction it's going in. And so if you can say how long it takes light to travel a distance, you know that distance. And the speed of light is a huge number. It's 3 times 10 to the 8 meters per second, and you can convert that to feet per second. A meter is 3 1/3 feet, so it's roughly 10 to the 9 feet per second, a billion feet a second. Or if you think about how far it goes in a nanosecond, it's about this distance. It's really, really fast. And so you can use that and divide this distance by the speed of light, and you get 500 seconds. So it takes light 500 seconds to get from the sun to you. And so if you're looking at the sun, and if you look at the sun, you should use protective equipment. I guess all of you know that because you're experts. But when you're looking at the sun, you're not seeing the sun in the present. You don't see anything ever in the present. You're seeing the sun 500 seconds ago in the past. If you're looking at your neighbor on your right, you're not seeing your neighbor in the present. You're seeing your neighbor probably 2 nanoseconds in the past. But your brain doesn't really care about nanoseconds, and so you build up this kind of incorrect intuition that you're seeing things in the present, and that's not true. And that becomes really, really significant when you're doing large distances. So we can step out from the sun and look at the next nearest star, which is a factor of 10 to the 5 away. And in light travel time, it's 4 years. So if you want to convert that into AUs, that's 200,000 AUs roughly. So even the AU is not a useful length unit for collections of stars. And so we introduce a new system of units for length for collections of stars and bigger objects. And that length is the parsec, which is abbreviated the PC, and it itself is an abbreviation of parsec, which is an abbreviation of a parallax of an arcsecond. And this is a cartoon demonstration of what a parsec is. You take your observer with a telescope and a protractor and send her so far away that this huge 1 AU distance here at this end of the triangle subtends 1 arc second at her. And there's roughly 200,000 arc seconds in a whole circle. And that's why roughly 200,000 AUs is 1 parsec. But probably the more useful thing about a parsec is that it takes light 3¼ years to travel that distance. And so that's an easy way to convert it to light travel time. And if you want to get a few numbers that we're familiar with, the moon is about 1 1/3 light seconds away. And that's the furthest we've sent humans. And I'm from Kansas, and Tombo is from Kansas, so I can use Pluto's orbit as a kind of a characteristic size for the solar system. And that's about that's about 6 hours in light travel time from Pluto to Earth. And the furthest we've sent anything are the 2 voyages. These numbers are from 2017, the 40th anniversary. And they've gone 19 1/3 hour. And it's not even 1,000th of a parsec. So with this kind of technology, if you want to get out to this guy, you can kind of really do a simple calculation and think about 40 or 50,000 years before Voyager gets to the next nearest star, if it's heading in that direction. So I want to spend a little bit more time walking out to larger scales. This is the Milky Way. And this is a really nice image. It's from the European Southern Observatory. You can find it on the web. Just put in ESO, Milky Way, and you can zoom in. It's not a very useful one to use for discussions. This is technology from 50, 60 years ago, same object. And this is probably the simplest one to discuss. So it's got a disk, and the diameter of the disk is 50 kiloparsecs, so 50,000 parsecs, or in light travel time, you take 50,000, multiply that by 3 1/4, and you get about 160,000 years. So if you could travel at the speed of light and you start here, it'll take you 160,000 years to cross this. And you can kind of compare that to 500 seconds to the sun from the Earth, or 4 hours, for 4 years from Proxima Centauri to the Earth. So this is a huge, huge object. It's got maybe 150 billion stars. And these stars are very heavy. The typical star mass is about half the mass of the sun. So they're pulling on each other gravitationally. And the fact that you see a disk is immediately telling you that there's something very, very interesting going on, because if there wasn't something interesting going on, all those stars would be gathered under gravity, and you wouldn't have this extended disk. And what's keeping this disk there is that the stars have kinetic energy. They have energy of motion. They're rotating. And so they can't get pulled in completely by gravity because there's conserved angular momentum. There's a bulge here, and the stars in the bulge are not systematically rotating. They're moving around randomly. They also have kinetic energy, so they haven't collapsed down to a point. And at the center of the galaxy, we have the nucleus, and that's where our big black hole lives. It's about 4 million times the mass of the sun. And it's actually a pretty small black hole on the scale of black holes at the centers of galaxies. The sun is about 1/3 of the way out. And this whole object is embedded in what's called a halo, which is probably about 1.5 million light years across. And it's kind of like a football, a squashed sphere. And that's got a lot of the dark matter, and there's a huge gravitational mass there, and there's a big potential well. And the shiny stuff, the atoms and molecules, they've collapsed down into the center of the halo, and they started shining because of electromagnetic effects. And they're globular clusters that kind of orbit in the halo. So we can go out and look at our next nearest neighbor, which is Andromeda. And that's also a spiral galaxy. You can see the spiral arms here because it's at an angle, and you can see the central bulge. Andromeda is a little bit bigger. In light travel time, it would take 200,000 years to cross it. And Andromeda is about 750 kiloparsecs away, or approximately 2.5 million light years away. So when you're looking at Andromeda, that light left 2.5 million years ago and traveled in a straight line from a star or hot gas and hit your retina and became an image in your brain. And that's kind of an interesting time scale for human evolution on Earth. Lucy, she's probably the most famous fossil, apparently climbed up a tree 3.18 million years ago in Ethiopia to get away from predators before going to sleep, and she fell out of the tree and died. And that was maybe 700,000 years before the light you're seeing from Andromeda now left Andromeda. So it's comparable time. So galaxies are really, really heavy. They're made up of 100 billion to 200 billion stars. And so when they come close together, they pull on each other gravitationally, and they form bound objects called clusters of galaxies. And this is the center of the Virgo cluster. It's a nearby cluster. And every dot of light you see here is a galaxy. These guys are in the foregrounds. You can see some spirals and ellipticals. And the scale here, it's a few megaparsecs, a few million parsecs. Capital M is million. So light travel time, maybe 6-7 million years to cross this. We can go out even further and look at this image. This is of the northern galactic cap. So what we're looking at is, I guess everybody knows there's a lot of dust in the plane of the galaxy, and it's easier and clearer to see stuff up here. And so they pointed the telescope up here and took images of that area. And this was done at Lick Observatory in the 50s and 60s by Shane and Virtanen. At that point, they didn't have CCDs. They had these big emulsion glass plates they put at the focus and then developed them. They didn't have laser scanners. So they took traveling microscopes and attached them to the end of these glass plates and looked through them and used paper and pencil to figure out the positions of 400,000 galaxies by hand. That was used to make this map. So the scale here at this distance from us is about 300 million parsecs, or in light travel time, about 1 billion years to cross this if you travel at the speed of light. That's the Coma cluster. It's got 4,000 or 5,000 galaxies, and it's just a few pixels here. You can see a whole bunch of other clusters of galaxies. And if you look carefully, you can see voids, these darker regions. And you can also see the one-dimensional filamentary structures. So there's a whole bunch of stuff going on here geometrically. And the easy way to think about this is lying back in your bubble bath in your tub at home. So you have bubbles, and the bright galaxies avoid the center of the bubbles. They hang out on the surface of the bubbles, and the centers of those bubbles are the voids. These are the dark regions, and they're dark because they're missing a lot of bright galaxies. And where two bubbles come together, you distort the bubbles, and you're looking at them in projection, so there's an enhancement in the number of bright galaxies that looks one-dimensional because of those two bubble surfaces coming together. And those are the filaments. And the filaments kind of drain into clusters of galaxies. You can kind of see there's a filament coming in here and one here and one here. And this kind of distribution has a name. It's said to be anisotropic. That's ANISOTROPIC. And maybe the better thing to do first is to understand what we mean by isotropy. So when we say something is isotropic, we're standing at one point and we're looking around us in all directions. And if it looks the same, then it's said to be isotropic. So you can do that in this room. You can look to your right and you can look above you, and you don't see the same person on your right and above you. So this room is not isotropic. If you get up 100 miles above the surface of Tucson, we can see the Pacific Ocean to the west, and you can see the Rockies to the east, and it looks different in different directions. The solar system looks different in different directions. You look in one direction, you see the sun. You look in any other direction, you don't see an equally big nearby star. And the same thing's true of the Milky Way. You look in one direction, you can see the central bulge of the Milky Way with lots and lots of stars. You look in the opposite direction, you don't see that many stars. And things are pretty anisotropic on this scale too. You look over here, you see the Coma cluster. You look over there, you see a void. And so maybe it's not that surprising because everything we're looking at is anisotropic. But things change when you go out another factor of 5 or 10. And this is the biggest scale picture we can currently take of the universe. This is the afterglow of the Big Bang. This was taken by the European Space Agency satellite called Planck, and it's a picture of the cosmic. So we're on really large scales, that's why it's cosmic. And it's microwave because that's that part of the electromagnetic spectrum, like wavelengths a fraction of a millimeter, much, much longer than visible light. And it's the background because it pervades everything, and it's radiation because it's electromagnetic radiation, and it's anisotropic. It looks different in different directions. So what this satellite had was a microwave detector, and you can kind of think of this from the position of the satellite. It's out there, and it's looking at the whole surface of the sky. And so you can kind of think of the surface of the sky as the interior of a big beach ball, and it's capturing light that's being emitted by that surface and coming towards the satellite. And it's taking that light and it's breaking it up into its spectrum. And from its colors, it can figure out the temperature of that light. And what I've done is I've sliced the beach ball from the North Pole to the South Pole and opened it up and spread it out over here. And so there's red hot spots and there's blue cold spots. And maybe the first thing we can do is ask for the average temperature across the sky. And that temperature is about 3 Kelvin. And that's in the scientific scale for temperature. So this room is roughly 300 Kelvin. So 3 Kelvin is very, very, very cold compared to the room we're in. It's almost absolute zero. And at 0 Kelvin, all motion stops except quantum mechanical uncertainty principle motion. So these guys, so you're familiar with microwaves if you cooked at home with a microwave oven, or if a police officer has given you a speeding ticket. So the way they give you speeding tickets is they take a microwave source and they send out microwaves and they bounce them off your car, and then they collect the reflected microwaves and they compare the pitch of the outgoing and incoming microwaves. And they use Doppler's formula to figure out how fast your car is moving relative to that microwave source. And all of you are familiar with the Doppler effect if you've noticed what happens when a fire engine or an ambulance goes past you with its siren on. As it's coming towards you, the pitch goes up, and as it goes past you, the pitch goes down. And so because the pitch is inversely related to the wavelength, when it's coming towards you, the wavelength gets shorter, and when it goes away from you, the wavelength gets longer. And because red light has longer wavelength than blue light, when things are moving away, you say they're red shifting. When they're coming towards you, they're blue shifting. And so this is the microwave background. The average temperature is about 3 Kelvin. And once we have that average, we might be interested in the difference between the hot spots and the cold spots. And the difference is 30 microkelvin, 30 millionth of a Kelvin. They're very, very similar in temperature. And if you compare that 30 millionth of a Kelvin to the average 3 Kelvin, then the bumpiness is 1 part in 10 to the 5, when you have 30 million divided by 3. Or in percent, the bumpiness is 0.001%. So the sky across here is different only to 0.001%. It's very isotropic. It's much more isotropic than it is on the scales of hundreds of millions of light years. So these are two really, really important facts about reality, that when we look out on smaller scales in our neighborhood, matter and radiation are distributed anisotropically in space. But when we get out to larger scales and average across them, the matter distribution and the radiation distribution becomes isotropic. And I'm not going to talk more about these, but if you're interested in how physicists try to rationalize these two facts, you can read up about the early inflation model of the universe, or inflation in the early universe. And Wikipedia and Scientific American and Discover and a lot of other magazines have really good articles. But you've got to be really careful what you look at on the web. So we've done the easy things, and now we want to move on to this other fact. And this is a really interesting fact, and it's more difficult to get a handle on. So I've got, I guess, I've got something pretty light here. So we have an expanding universe. At least we claim to have an expanding universe. So that must imply that we have measuring devices that are not also expanding in exactly the same way. And so here's my measuring device, and I want to kind of talk about why this might not be expanding the same way as the universe is expanding. So we know what the important forces are on macroscopic scales. There's gravity, right? So if I have a mass and I don't support it, it's going to be attracted by the Earth, and it's also going to pull the Earth up towards it. And we know what the law is. So if you have two masses, then the gravitational force between them is proportional to each of their masses, and it's also proportional to Newton's big G, and it's inversely proportional to the square of the distance. So if you double the distance, then you get a 2 squared in the denominator, which is a factor of 4. So the force goes down by a factor of 4. If you triple the distance, you get a 3 squared, and you get a 9 in the denominator. The force goes down by a factor of 9. So gravity is always attractive. When we drop things, we don't find them floating upwards because gravity is attractive. The other important force on the scales of these objects is the electric force. And the electric force also obeys an inverse square law type of force law. But it's a little bit different than gravity. That's because there's two kinds of charges. There are negative charges, and the electron is an example. And there are positive charges, and the proton is an example of that. And we know that like charges create electric fields that push themselves apart, and unlike charges attract each other. So if you have a proton and an electron, they attract each other. And if you have an electron and an electron, they push each other apart. So if you have two protons, gravity is going to pull them together, and the electric force is going to push them apart. And does anybody have a feeling for the relative strength between the electric force and the gravitational force? Is gravity much stronger than electricity? Who thinks gravity is stronger? Who thinks, okay, one. Who thinks electricity is stronger than gravity? 10, okay. And half the audience is really shy tonight. Okay, so yeah, the electric force is way, 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 way stronger. So if you take two protons, they're going to be pushed apart by a force that's 36 powers of 10 stronger than the gravitational force pulling them together. So you're made up of atoms and molecules, and you also have mass. So are you repelling your neighbor gravitationally? Anybody think you're repelling your neighbor gravitationally? So are you attracting your neighbor gravitationally? So who thinks you're attracting your neighbor? Can you put your hands up? Okay, and it's a very weak force because your mass is so tiny. If you scale up your masses to the size of planetary masses, you'd pull on each other much, much stronger under gravity. So what about electricity? Are you attracting your neighbor electrically? Are you repelling your neighbor electrically? Nothing's happening. So you're basically neutral. You're made up of molecules, or if you want to think about it in terms of atoms. And atoms have nuclei that have protons and an equal number of negatively charged electrons. So your electrons are pulling your friend's protons towards you, and they're pushing your friend's electrons away. And those two forces cancel. But there's a couple of exceptions. Did anybody bike in today? So you might have built up some static charge on you. Okay, maybe if you comb your hair really vigorously, you'd build up static charge, and then there'd be a residual electric force. But there's almost no electric force between you and your neighbor, even though the electric force is much, much stronger than gravity because bulk matter is neutral. And so even though the electric force is so much stronger, by the time you get to planetary size objects or galaxies, gravity is going to dominate because everything's neutral. And so if you want to talk about very, very large scale things in the universe, which is what we want to do for cosmology, we need to have our most accurate model of gravity because that's the only force that's relevant on really large scales because everything's neutral electrically. And so we can go and look at what models we have for gravity. We have Newton's model for gravity, where he had falling apples happened to fall in a fixed space, and time ran uniformly. It didn't get affected by what the apple was doing. And he came up with this inverse square law of gravity. And this was in the 1600s. And then Einstein realized in the 1900s that he could improve on Newton's description of reality, and his description of reality worked better when things were moving at speeds close to the speed of light, or when things were on very, very large separations, or in very strong gravitational fields. And what Einstein did was he made space and time participate in the dynamics of physics. So as the apple was falling, it would also deform the space in which it lived, and it would change how time ran. And Einstein ended up developing what's called the general theory of relativity. And that it's a mathematical model. It's a collection of partial differential equations that are nonlinear and coupled. And the way you build up intuition about that is you go and solve those mathematical equations, and then you make predictions, and you compare those predictions to measurements. And if they agree with the measurements, you're happy, and you start developing some intuition for general relativity. But some of you probably have not solved the general relativity equations. So what I'm going to do is I'm going to solve the equations for you, and I'm going to translate those solutions into English. And that translation is very inexact. So we have to be a little bit careful. So I'm going to start out. So we live in a three-dimensional space. So there's two horizontal dimensions and one vertical dimension. And I'm going to start out with a one-dimensional space first. And what I have here is a one-dimensional space, because I'm going to ask you to ignore the width of this band and just focus on the length here. And I can have my measuring device, and if I choose my origin over here, I can measure down here, and I can tell you how many centimeters away this point is, and I can give you all the information you need about distances. And my measuring device is held together by the electric force, and Einstein's going to come along, and he's going to start creating space, because space is now dynamical. And I've got a wave here, and you can see the peaks and troughs, and I can measure the wavelength with the measuring device. And as space expands, or space is created and the universe expands, the wavelength gets bigger and bigger. It gets longer and longer. So if you start out with blue light, which is short wavelength, and you go enough, it could turn into red light. And that gives you some idea of how we're going to be able to show that the universe is expanding. So we have to be very careful with this. There's no edges to the universe in the simplest model that fits the observations. Because if there was an edge, you could walk to the edge and look out, and outside would look different than inside. It wouldn't be isotropic. And I told you it's isotropic. And so the way you make it isotropic is to send the edges out to infinity. And once you push them out there, there's nothing outside. And so you don't have to worry about that. And general relativity doesn't go to the edges of space and start pulling. What it does is it goes into space, it creates new space, and the old space that's there doesn't appreciate that new space, and that new space has to go somewhere, and everything that lives in that new space and that area gets taken along for the ride, and that's the expansion of the universe. And the guy who first saw the effects of this expansion did this at Lowell Observatory. Or maybe I'll go over this one a little bit and introduce a little bit of math. So, so this is the band at an earlier time, and this is it at a later time, and we'll call this the present time. And we've got a wave on here. It has a wavelength lambda naught in the earlier universe, and as time goes on, that gets stretched. And the distance between the hands gets bigger and bigger. And we need some way to characterize the local size of the universe. And so we can loosely think of that as the distance between the hands. And cosmologists will call this the scale factor, and they use the symbol A for it. And it's a function of time. So as time gets bigger and bigger, the scale factor gets bigger and bigger, and the wavelength gets bigger and bigger. But astronomers don't like using the scale factor. They prefer using the redshift, which is this variable z. And the way that's related to the scale factor is through this equation. 1 plus z is the value of the scale factor now. That's this guy, relative to the value of the scale factor when that light was first emitted. So if we choose to emit the light at the present time, then the scale factor in the denominator A of t is going to have the value A of now, and the right-hand side is 1. And so 1 plus z is equal to 1, so z has to be 0 over here. But as you go back to the early universe and emit the light there, then A of t, when you emitted the light, is smaller than A of now. And so this is bigger than 1, and z is bigger than 0. So the redshift, the redshift is 0 now, and it's large in the past. Time is small in the past and large now. Scale factor is small in the past and large now. Wavelength is small in the past and large now. And we can now go to Slipher, and some of you, or probably all of you, have seen this telescope. It's at Lowell. So Slipher pointed this at galaxies. He passed the light through diffraction gratings, broke it up into its spectrum, and from the ratios of spectral lines, he could identify the elements that produced these lines. And then he went and looked at their spectra in the lab, and he found the spectra in the lab were shorter wavelength, than the spectra he was seeing through the telescope. So he was seeing the red shifting. And the next step that happened was, okay, so the red shifting. So there's two ways of thinking about this. It could be that you're seeing this Doppler effect, right? So things are moving away from you. And one way to think about this was that there was a big firecracker at one point in space in the past, and everything started moving away from there. And by coincidence, Slipher ended up at that point in space, and he could see everything moving away. But that's not what's happening. Something else is happening that's even more interesting. What's happening is that at one instant of time, every point in space started moving away from every other point in space. And it doesn't matter where you are, you'll always see that every other point is moving away from you once that starts up. And so I want to back up a little bit and tell you a little bit about galaxies, the mature galaxies. After galaxies have formed, and these are the galaxies that are my ping pong balls, they don't expand with the expansion of the universe. What's happening is the space between them is expanding, but the galaxies stay fixed in size. And so we can look at this image up here. So this is a flat universe. It's a three-dimensional flat universe. It's a Euclidean space. It's got 3 axes. And this has just got to be a chunk of the universe because of the same argument. If you go to the edge and look out, it'll look different when you're looking out than when you're looking in. And so the way you make this isotropic is you send it out to infinity in all 3 dimensions. And so as the yeast rises, my chocolate chip galaxies are going to move apart. And we can ask an observer on galaxy number 2 what she sees. She'll tell you she sees every other galaxy move away from her. And an observer on galaxy number 4 will tell you exactly the same thing. So every galaxy moves away from every other galaxy, and that looks the same no matter where you are. And it doesn't imply that you're at the center of the universe. Every galaxy, every point in space moves away from every other point. So after Slipher did those observations, Hubble, who had access to a much bigger telescope, this is the one at Hale Observatory outside in the San Gabriel Mountains outside the LA basin, he could collect much fainter objects with this, and he found a whole bunch of Cepheid variables in these galaxies Slipher was looking at. And these Cepheid variables are very, very useful stars because of a discovery Henrietta Leavitt had made in 1907 or 1908. And she had discovered that from the periodicity, you can figure out the absolute luminosity of these stars. And so once you know the absolute luminosity, you can use your photometer and get the apparent luminosity, and then you can get the distance to these stars. So Hubble was able to use Leavitt's law to get the distances to these galaxies, and he found this really nice linear relation between the recession velocity and the distance. It's a linear one, and so a galaxy twice as far away will be moving twice as fast. A galaxy 3 times as far away will be moving 3 times as fast. And astronomers are a little bit strange. They measure velocities in kilometers per second, but they measure distances in megaparsecs. So you can tell that this is distance divided by time. That's distance. So the Hubble constant, which is the constant of proportionality, has units of 1 over time. but because of their units, its units are kilometers per second per megaparsec. And this is sort of the value of the Hubble constant. And you can kind of see proof of this. This is a famous graph from the group that was led by Wendy Friedman. She was one of the PIs of one of the key projects on the Hubble Space Telescope. And the Hubble Space Telescope was built to improve the measurement of the Hubble law. And these are the recession speeds up here, 10,000 kilometers a second, 20,000, 30,000. And these are the distances here. The numbers are down here. So a galaxy 100 megaparsecs away is moving away at about 7,000 kilometers a second. A galaxy 200 megaparsecs away is moving away 14,000 kilometers a second. And this solid red line was the best fit to Hubble's law then. And so we have these guys moving. So maybe I'll do this balloon demonstration also a little bit. It's a two-dimensional demonstration because I can't do the three-dimensional space here. But you've got to think of yourself as a little ant that lives on the surface of this balloon. And you can't go into the balloon and you can't come out of it. So all you can do is you can walk along it. And if you're a rich ant, you can buy a rocket and travel along it with the rocket. But if we look at what's happening here and focus on one of these galaxies, so I'll just turn this off. And you can think about what's happening. So if we're on this galaxy with our telescope and we're looking at this galaxy and it emits blue light, that light's going to travel at the speed of light, and it's going to cross a small patch as more space is being created as the universe is expanding. And its wavelength gets stretched a little bit, so it gets a little bit of a reddish tinge. And if you look at the further away galaxy, it has to cover more distance for that light to get here. And it's going to be a little bit redder. And you go to further away galaxy, it's got a bigger distance to cover, and it'll be even redder. And finally, it'll be red and then infrared as you get further and further away. And it doesn't matter what galaxy you live on, as long as you ignore this neck, there's no special thing about a galaxy on this balloon. Any galaxy, any observer on any galaxy will see the same thing. The observers that won't see the same thing are those that have rockets, because they're moving and they'll see the Doppler effect and the front and back will look different. And those guys won't see an isotropic distribution. And that's why we need to be really careful about what observers we use in cosmology. And so we have these guys we call cosmological observers, and these are the guys that are at rest with respect to expansion. They're sitting on here, and they don't move on the surface. And those guys are the ones who see isotropic distributions around them. So once you know that any observer is an equally good observer, what you're doing is you're standing over here and you're looking around and it's isotropic, and then you meander over to Andromeda and you do the same thing and it's also isotropic. There's a theorem in geometry that tells you you're in a system with much, much bigger symmetry, and that symmetry is homogeneity. And the simplest example of homogeneity is putting on your scuba suit and jumping into a gallon jug of milk and swimming around. And it's going to look exactly the same whiteness as long as you don't get to the edge of the container. So once you know it's homogeneous, there's only three possible geometries. We're all familiar with the flat geometry, like the top of this table. And in 3 dimensions, it's this room, it's Euclidean. And that's this guy. It's got to go out to infinity in both dimensions. And it's got zero spatial curvature. And we talked about the 2-dimensional geometry of the sphere. That's the surface of the sphere. And as time goes on, this gets bigger and bigger and bigger. And that's a closed geometry and has positive space curvature. And we can also have negative space curvature, and that's hyperbolic. And it's got to go out to infinity, and that's called the open geometry. And these guys are the density parameters, and I'll come back and explain what they are. But all you need to know here is that this is the critical density, this is underdense, and this is overdense. So the way to think about this is to think about the scale factor as being the radius of this balloon, and as time goes on, it gets bigger and bigger. And that's our dynamical variable. And the equations that we get for that dynamical variable come from general relativity. And general relativity, what it's doing is you have a gravity, you have the mass. The mass acts as a source of a gravitational field. And what that gravitational field is doing is it's creating more space. And I don't want to talk about the whole universe because it could be infinite and then it have an infinite amount of mass. So what I'm going to talk about is a little local area here and look at the mass per unit area. In the three-dimensional case, it'll be the mass per unit volume, and see how that creates a gravitational field and how that gravitational field creates space. And so I'm going to talk about everything in terms of density or mass energy density. So we know, so the dot just means the rate of change of this with time. It's the speed of the expansion. And we know that speed is positive because everything's moving away from us. So the next question we might ask is, after she started driving the car and moving away from the garage, is she going to hit the brake and then she keeps going, but she goes away slower and slower and slower and then eventually stops? Or does she hit the gas and does she keep speeding up and moves away faster and faster? So does the expansion of the universe decelerate or does it accelerate? And the easy way to think about this is in terms of a messy equation, which I've written down here, but you're all very familiar with the version of this equation. It's Newton's F equal to ma, but I've written it with the m in the denominator. I've written it as a equal to F divided by m. And it's very, very unfortunate that in Newtonian physics, a is the symbol for acceleration, while in cosmology, a is the symbol for the scale factor. So I'm not going to use a for acceleration in cosmology. I'm going to put two dots on top of it, and that's the acceleration of the expansion. And we can see immediately, well, let's just ignore all this stuff over here. But we can see that the gravitational field is created by the mass energy. And we have Newton's big constant here, and we have a minus sign here. And it's really easy to understand that minus sign. So if you think about what's happening here, I can't give you a really accurate model of what's going on. But if you think about these two galaxies, they're not actually fixed in space. So they are sitting here, but they have mass. And Newton's going to tell you that they're going to attract each other with his inverse square law force. And so they're going to try to move towards each other. So I don't have enough money to make an analog demonstration of that. But these galaxies are moving on the surface a little bit. And Einstein's coming along, and he's saying in regions where there's things that are more homogeneous, he's going to create some space, and he's going to push them apart. So if these galaxies have more mass, then Newton's attraction is going to overwhelm Einstein's space creation process. And that's what this minus sign is telling us, that we have expanding universe. We've started out the Big Bang, and she's hit the brakes. So there's a deceleration. It's a negative acceleration, and it's slowing down. So then we can go back and put in the pressure. And the pressure is just a measure of the kinetic energy. It's how much motion energy there is in these galaxies that are moving over on the surface. That's why there's a 3, because there's 3 space dimensions. And if I wasn't working in natural units, I would have the speed of light squared in the denominator, and that's a relativistic effect. And you know where that's coming from. It's just Einstein's E is equal to mc squared. So if you have kinetic energy, then you divide that by c squared, and that's the associated mass with that kinetic energy. And that mass will then act as a source for the gravitational field. So if you have energy of motion, you get an extra contribution. And for those of you who are familiar with general relativity, this is the active gravitational mass density. And so it contributes and it slows down the acceleration even more. It gives you a bigger deceleration. So you go and tell your astronomer friends that you can strongly predict this deceleration, and they go out there and measure a double dot, and they find that a double dot is actually positive. And that's a big problem. You can either discard general relativity, but if you're somewhat conservative and you realize that general relativity works very well for gravitational waves, it works very well for black holes, that's not the first step you want to take. And you want to try to introduce a new hypothetical substance to try to patch up general relativity and these observations. And that hypothetical substance is called the cosmological constant of dark energy. It comes in with the same sort of form as the matter, the cold dark matter and the baryonic matter, and it comes in with the lambda energy density and the lambda pressure. But the main difference is that the equation of state, the pressure for this is negative of the energy density. So rho lambda plus 3p lambda is a negative quantity. And if you make rho lambda bigger than rho matter, you can have everything inside the parentheses be negative, and that negative sign cancels that, and you get accelerated expansion, and you can agree with what the observers are seeing. And it would seem to be a very, very stupid thing to introduce this hypothetical substance to patch up your mathematics. But it turns out that you can measure this dark energy in half a dozen different ways, and the measurements are all roughly consistent. And so maybe it's not completely crazy. And when we get better data, we'll see what happens. But maybe I should stop here and answer questions if people have questions. Thank you.
Thank you very much, Batra. We actually have time for some questions. If you're listening on Zoom and you have a question, just type it into the chat box and we'll read it out. Do we have any questions from the local audience? Yes.
If the universe is slowing down, would that affect the passage of time so that time would be speeding up over the 13 billion years since the Big Bang?
For the cosmological solutions of general relativity, time is pretty unimportant. It kind of runs fairly uniformly. But the space geometry is more interesting. But if you're talking about black hole solutions, then time kind of varies depending on what's happening to you as you're falling in, and it's more important there than it is in cosmology. And it's not slowing down, it's accelerating, it's speeding up.
Other questions?
So you're talking about dark energy and dark matter together as if they're the same type of thing. Is that the case?
No, they're not the same type of thing. So there's a bunch of differences. So the best models we have for dark matter is that they're particles, and they're probably 10 or 100 times as heavy as protons. But for dark energy, it's either this cosmological constant, and we see things like this in the lab, and they're typically always associated with zero-point quantum mechanical fluctuations. So one example of this in the lab is what's known as the Casimir effect, where you take two parallel metal plates and you solve Schrodinger's equation for those boundary conditions. And you can see that the zero-point fluctuations act like a force on these metal plates. And that has an equation of state of this form, P equal to minus rho. And we see this in the hydrogen atom, the Lamb shift of the hydrogen atom when we do the nucleus modeling of the hydrogen atom more accurately. So the hope is that there's something like this happening that's related to quantum mechanics on very, very large length scales, but we have no evidence that that's true at this point. And if it's made up of a scalar field or a dynamical field, then the particle masses associated with dark energy are very, very, very tiny. So dark energy is very relativistic, unlike dark matter, which is made up of heavy particles that behave very non-relativistically. And those dark matter particles typically are thought to travel at a few hundred kilometers a second, while the dark energy particles would have speeds close to the speed of light. And because they're moving so fast, they're pretty uniformly distributed on very, very large scales, up to hundreds of megaparsecs. While there's dark matter all around us now, there's concentrations of it, I mean, in the halo. So the dark matter is collected on much, much smaller scales. It's bumpier on smaller scales. than the dark energy.
We have a couple of questions on Zoom. Oh, we have some more. So let me go back up to the first question. It was, why are some galaxies blue shifted?
So Andromeda is blue shifted. It's very, very close to the Milky Way. And you can accurately model the Milky Way Andromeda system using Newton's inverse square law for gravity. And they're traveling towards each other. And in the simplest models of this Andromeda Milky Way system, they're probably going to merge with each other in maybe 5 to 10 billion years. And because they're traveling towards each other, that's why they're blue shifted. And
Is dark energy accelerating the expansion of the universe?
yes, dark energy is the substance that's been introduced to cause the observed acceleration of the universe.
Okay, do you think that in the next decade or two, we'll have proof of dark matter?
I hope so, but I mean, it's kind of instructive to think about what's happened in the past. So in the 1930s, when people were doing scattering experiments in particle physics, they were seeing signatures that apparently seemed to suggest to them that energy and momentum were not being conserved because they could count the energy and momentum that was being carried out by the particles in these scatterings through the detector. And Pauli got really upset with this because he thought energy and momentum conservation were really fundamental. And so he suggested that there was a particle that eventually got called the neutrino that interacted extremely weakly with the detectors they had in the 1930s. And so that it was escaping without being detected, and it was carrying away energy and momentum. And it took almost a quarter century before people could build sensitive enough detectors to detect the neutrino. So if dark matter interacts even weaker with our detectors, it's going to take quite a long time to be able to find it through particle physics experiments. And it's been, in some sense, it's been around since the 1930s, but people didn't really take it seriously until maybe the 1980s. So it's only been really looked at very seriously in the last 30 or 40 years, even though it's been around for maybe 80 or 90 years.
And we have one last question on Zoom. I've read that some cosmologists believe the universe is older than the estimate of 14 billion years due to effects of something called tired light. What's your view of this hypothesis?
So this was an idea that Zwicky also introduced. So Zwicky was the first guy who suggested there was dark matter. He was looking at clusters of galaxies and seeing how fast galaxies were moving, and from that he concluded there was dark matter. But he also wanted to try to explain this redshifting as saying that light was losing energy as it was propagating. And most cosmologists now no longer think that's a valid explanation for what's happening. They think the redshifting is consistent with the universe being about 13.75 billion years old, and that there's no evidence for tired light.
Okay, now one last question, and then we have to move on.
How did we determine that our observable universe has a flat curvature omega equals 1 rather than an open or a closed curvature?
How do we know that it has flat curvature? So that's the simplest model that works at explaining all the data. And so what's driving that mostly is the bumpiness in the microwave background, those red and blue spots. And that power there changes. There's going to be peaks. So that bumpiness is coming from physics. So when the universe gets really hot, you no longer have atoms because you have so much thermal energy that you split the atom up into nuclei and electrons. And electrons tend to couple very strongly to photons. So photons are the quanta of the electromagnetic field. And that's what we're seeing. We're seeing the microwave background. That's the electromagnetic field we're seeing. So these guys these photons are coupled to the electrons. And as gravity starts pulling stuff in, because gravity is attractive, so you have a bunch of photons and you have a bunch of electrons, you kind of pull this stuff in. But those photons, because they're coupled to the mass of the electrons, they resist and they want to push it out. So gravity pulls stuff in and then it bounces and it pushes it out. And so you get acoustic oscillations in the universe, in the early universe. And those acoustic oscillations have harmonics. And you're seeing basically the peaks of those harmonics, and they're damped. So if you have a fundamental, that fundamental tells you something about the size of your instrument, and it tells you something about the tension in the string and the geometry of that string. And that's related to the geometry of space. So depending on whether it's open or closed, the frequency of that fundamental in the power spectrum is different. And you can measure that, and the Planck satellite measured that accurately. And they give you a value that's very close to a flat geometry.
All right. The Tucson Amateur Astronomy Association is going to continue with their meeting at this point. For those of you who are only here for the public evening lecture, you're free to go. But I want to remind you that our next public lecture is on St. Patrick's Day. It's on Monday, the 17th of March. Our founder, Professor Douglas, also invented the science of dendrochronology, and he founded the Laboratory of Tree Ring Research after he stepped down as director of Stewart Observatory. We have a member of the faculty of the Laboratory of Tree Ring Research on the 17th of March who's going to give us a talk about how she has been able to find evidence of massive solar flares in the tree ring data. So let's thank Professor Ratra one more time. And the Tucson Amateur Astronomy Association will continue with their meeting.
Thank you very much. It was a pleasure.
There's that. I'll just give you this microphone.
And on behalf of the Tucson Amateur Astronomy Association, I want to thank you so much for sharing your presentation with us. We just thoroughly enjoyed it, and it was just such a privilege to be able to be here. So thank you so much.
Thank you very much. It was a great pleasure to be here and to allow me to share this with you.
So we hope if you come back at some point that you will visit us as well.
Yeah.
Wonderful. Thank you. Okay, everyone, I think we're back to our Tucson Amateur Astronomy group. And this was a wonderful presentation. So again, we're so glad that we were privileged to share it tonight. We do have another presenter tonight. Eric Rakashka is here. He's going to do his monthly planet report for us. And a reminder to everyone, Eric's planet report is on our website. He posts it every month so that if you forget during the month things that you want to look up that has shared here, then you can find them at the moment that you need them. So, Eric, thank you.
Well, about a week ago, we had all the bright planets in the evening sky lined up, but Saturn was soon lost, and within this month, we'll also lose Mercury and Venus. So Mercury is still very well visible in the west around 7 p.m. It's visible until the 13th, so another week or so. And during this time in telescopes, it will show a nice crescent, although you need some magnification to do that. Venus was very high up in the evening sky for several months, but this is the last one that's visible in the evening. The last day to see it naked eye will be the 19th. So right now it's still very bright, but within 2 weeks it will be too close to the sun. And then on the 21st of March, it will start to be visible in the morning sky. So that 20th of March, the equinox date is the only day where you cannot see Venus naked eye. It just switches from the evening to the morning. And in the 20th, you may be able to see it in binoculars, of course. And it switches so fast from the evening to the morning side because it's 8 degrees north of the ecliptic. Other planets really don't make it that far off the ecliptic. They stay within a few degrees. But Venus every 8 years gets to 8 degrees. And if you look in the evening sky and you see Mercury in the west around 7 p.m. and Jupiter is still high up in the south, so it goes really very steep up. But Venus is quite far off the line. So Venus just is really not in the ecliptic right now. And Mercury is still prograde, but Venus is retrograde. So even though they are far apart this week, well, actually, they are not that far away. On the 8th, so just in a few days, they'll meet each other, but the distance still will be 7 degrees because Venus is so far north of the ecliptic. And if you watch Venus in a telescope, it's 60 arc seconds in diameter, so it's as large as any planet can get around the third week of March when it gets closest to Earth. And it's an extremely thin crescent, but it's not just the crescent, it's it goes more than 180 degrees around when it's so close to new Venus phase. So when within a week or maybe even a week and a half of that date, 22nd of March in telescope, you would see maybe a 3/4 circle or 2/3 of a circle. And that's how you can see that Venus has an atmosphere, because a planet without atmosphere wouldn't do that. And Venus is, of course, pretty low in the morning sky in the day, but you maybe also be able to find it in the daytime if you know where to look. And then, so Jupiter is very high up in the southwest when it gets dark, and it's moving prograde close to Aldebaran. And Mars is the other planet that's still visible for a while. It's magnitude 0 and 10 arc second in diameter. So it's still a nice object in telescopes. You still can see surface features. It wanders near Pollux, and it's very far north, 83 degrees high in the south at around 8 p.m. One other planet for binoculars, Uranus, is 6 degrees south of the Pleiades, and it will actually get even closer to that, but the Pleiades are getting lower and lower in the evening sky. And another planet, a minor planet, is also in the late evening sky. It rises around 10 p.m. in Libra. That's the minor planet Vesta, number 4. And it will still become brighter in the next month or two, so it will become actually just barely naked eye. The main event this month is the total lunar eclipse in a week, about a week from now, on the evening of the 13th, morning of the 14th. The totality lasts 66 minutes from 11:26 to 12:32. So it's centered exactly on midnight, maybe 1 minute before midnight. Full moon is 5 minutes before midnight. That's because full moon is not defined that way when the moon is full, but just a little off. And the partial phase lasts almost from 10 p.m. to 2 p.m., so 4 hours, if you can stay up that long, from 10 p.m. to 2 a.m. So the weather forecast is not ideal for the 13th, so we'll see, but somewhere it will definitely be clear, and so I hope we can see it too. Thank you.